Okay, in today's lecture, we're going to cover the section 13.4 material on area and something called the definite integral. So to introduce the main idea for this section, let's pose a question. And this was one of the two questions that led to the development of all of calculus. So here it is. Let's suppose that we have a function f, which is non-negative and continuous on some interval from a to b. So let's sketch the graph of this. Maybe we've got some function in the first quadrant. So maybe it looks something like this. Let's say this is the graph of y equals f of x. And we're looking at this function, which is continuous and non-negative, so it lies above the x-axis on this interval from a to b. So the question of interest is, what is the area of the region, let's call it R, which lies under this curve and above the x-axis from x equals a to x equals b. So if we consider on our interval from a to b, dropping these little vertical lines down to our curve, from our curve to the x-axis, we have some region R, shaded region here. And the question is, what is the area of that region? So we know how to find the area of certain regions, say if they're shaped like squares, rectangles, circles, triangles, and so on. But for a more abstract region like this one, how could we determine the area of such a region? So in order to try to answer this question, let's see if we could just approximate the area of this region. So in order to keep track of what I'm doing in our further discussion, let me draw this same figure below to illustrate how exactly this is going to work. So just copying the figure that we had above. In order to approximate the area of this region, we will start by dividing our interval along the x-axis, that is from a to b, into n equal subintervals, which would have length denoted by delta x. And so if I'm dividing this into n equal subintervals, well, I would take the total length of my interval from a to b, which would be b minus a, and then I divide it up into n equal pieces. So what I'm doing is taking my x interval from a to b, and I'm going to divide it up into little subintervals of equal length. So the length of each of these intervals is what we're calling delta x. And there are n total intervals. So the more subintervals I use, of course, the smaller the length of those intervals. So the intervals that we're considering are the following. The particular subintervals are from a to a plus delta x, then from a plus delta x to a plus 2 delta x, and so on, up through our last interval, which would go from a plus n minus 1 times delta x to b. So this last little interval where we hit our right endpoint b. So we can think about each of these subintervals as forming the base of some rectangle. So if we consider each of these little subintervals as the base of a rectangle, then we could denote the endpoints of these n subintervals as x1, x2, up through xn plus 1. So the endpoints of my intervals, we could take either the left or the right endpoint. So maybe if I took my left endpoint, then we can use those endpoints as the heights of an approximating rectangle, which would be given by the height of the graph of the function at xi. So that is f of xi. So for my first endpoint, x1, I'll choose the left endpoint of my first interval, and then I can evaluate the value of the function at that point, f of x1. It would be the height of my function, and I'm going to use that as the height of a rectangle whose base is the length of this first subinterval. So I would have a little rectangle shown here. Now for my second point, x2, the left endpoint of my second interval, I could take the height of my rectangle as f of x2, where the base of the rectangle is the second subinterval, so I have this little rectangle. And so on. I could keep constructing these values, and I would have a bunch of little rectangles which are sort of overlapping the area of this shaded region that we're interested in. But now we know how to find the area of these rectangles. In particular, the area of the ith rectangle is denoted as a sub I, and it would be found by taking the height of that rectangle, so that is the value of the function at x sub I, so for instance this height, say f of x sub 1, and then we would multiply by the width of that rectangle, which is delta x, the length of any one of my subintervals. So to approximate the area of R, the shaded region that we're interested in, I could add up the area of each of these little rectangles, and it would be an approximation of that shaded area. So here the total area under the curve can be approximated by something called a Riemann sum. So this is the sum of the areas of our rectangles, which were given by f of x sub I times delta x, and then we're adding up the area of each of those rectangles, starting with our first rectangle up through the nth rectangle. So that would be the sum of the heights of my rectangles, f of x1, f of x2, up through f of xn, times the width of those rectangles, which are all delta x. So the exact area of this region R could be defined as the limit of this Riemann sum as the number of rectangles gets larger without bound. So we can see from our figure here that by using these rectangles, we get an approximation for the area of our region of interest, but it's not exact. However, if I were to use a lot of rectangles that have very thin width, then I see I could fill in my shaded region R much more precisely. So even the way that I'm drawing this one would not be a perfect value for the area, but let's say we divided each of those little rectangles into smaller and smaller pieces. So as the number of rectangles that I use becomes larger and larger, and the width of these rectangles is getting smaller, so that we're filling in our area precisely, we would get the true area of our region. So here we define the area of the region under our curve as the limit as the number of rectangles n approaches infinity of our Riemann sum. So we're taking the sum of the area of all of these rectangles and letting the number of rectangles approach infinity. And this is what we will define as the area under that region, provided that this limit exists. So recall from our chapter 11 material, not all limits exist, but if this limit does exist, then that will be our value for this area. So that leads to the following definition. If f is a continuous function on the interval from a to b, then we define the definite integral of the function f from a to b as follows. So the notation that we use is very similar to what we had for the indefinite integral. We have this sort of elongated s, which is called the integral sign. We have the function f of x that we're considering the area under, which is a function of the variable x. So our dx on the end is used to denote which variable we're working with. And then on our integral sign, we have a subscript and a superscript, a and b, which are used to denote the left and right endpoints of our interval of interest. And this is defined as that limiting value of our Riemann sum, where delta x is the length of one of my subintervals, b minus a over n, and x sub I, the value that I'm evaluating my function at, is the left endpoint of the ith interval, provided that this limit exists. So we now have a definition of the definite integral of a function from a to b, which represents the area under the graph of that function and above the x-axis over our x interval from a to b. Now a little more terminology here. We would say if this limit does exist, then the function f is said to be integrable over the interval from a to b. The function f of x that we're considering the area under is called the integrand, and the numbers a and b, those are the left and right endpoints of our interval, are called the limits of integration. So let's look at some examples where we will approximate the value of a definite integral by using a Riemann sum, so that is by adding up the area of some approximating rectangles, where we're using a predefined number of these rectangles. So in our first example, we are asked to approximate the area that lies under the curve f of x equals x squared plus 1, and above the x-axis on the interval from -2 to +2 by using rectangles whose height is the value of the function at the left side of the rectangle. And in part A, we're told to use 2 rectangles. So before we jump into this problem, let's just look at a sketch of the region that we're interested in. So here we were looking at the region that lies under the graph of x squared plus 1, which is a parabola whose vertex is at 0, 1, and is opening upward. And we're looking at the graph of this function on the interval from -2 to +2. So the area of interest is the area that lies under the graph of that function and above the x-axis over this interval. So here our curve was x squared plus 1. So now, in order to find this area, or to approximate this area, we're told that we're going to use two approximating rectangles. So in order to find the base of these rectangles, we're going to take our total interval, which was from -2 to +2, and divide it up into two equal subintervals. So the length of those subintervals is what we were calling delta x. It's found by taking b minus a over n, or in this case, b was 2 minus a, which was -2, so we're taking the right endpoint of our interval minus the left endpoint. And then we're dividing this into two equal rectangles, or two equal subintervals. So we have 4 divided by 2, which is 2. So the intervals which will define the base of our rectangles are from -2 up to 0, and from 0 to 2. So here we're taking our total interval, -2 to 2, and we're dividing it into two equal pieces. So here delta x was 2, so we're moving from -2 to 0, and then from 0 to 2. So these subintervals will be the bases of our rectangles, and we're told that the height of the rectangles are given by the value of the function at the left side of this rectangle. So here the left endpoints of these intervals are our points of interest. So here let's say the left endpoints are x1, the first one is -2, and x2 would be 0. So that means that the heights of these rectangles are the values of the function at these endpoints, that is f of -2. So substituting -2 in the function x squared plus 1, we would have -2 squared, which is 4, plus 1 gives us 5. And f of x2, which was 0, substituting into x squared plus 1, we have 1. So the area of this shaded region can be approximated by taking the area of our two rectangles. So here f of -2 we said was 5, and then f of 0 is 1. So we're taking the rectangle which has the width of delta x and whose height is given by the value of the function at these left endpoints. So we have these two rectangles. We're going to add up the area of those two as an approximation of our shaded area. And we can see from our figure here that it's probably not the best approximation. But nonetheless, for the area of our first rectangle, well, the base width was delta x, or 2, times the height of our rectangle, which we found to be 5, plus the width of our second rectangle was also delta x, which was 2, times the height of that rectangle, which we found to be 1. So we have 10 plus 2, or 12, for the approximate area of that shaded region, 12 square units. Now in part B, we're told to approximate that same area, but now using 4 rectangles. So here, let's approach this the same way. The width of each of our subintervals, delta x, will be the total length of our interval. So right endpoint minus the left endpoint, 2 minus -2, and we're dividing this into 4 equal pieces. So we have 4 over 4, or 1, for the length of our interval. So let me illustrate here. We're looking at the same function, y equals x squared plus 1 on the interval from -2 to +2. And we're supposed to divide this into 4 equal rectangles. So the length of each one is going to, or the base of each one will have length 1. So we're going to go from -2 to -1, -1 to 0, 0 to 1, and from 1 to 2. So here the intervals, which are defining our rectangles, are from -2 to -1, -1 to 0, 0 to 1, and 1 to 2. So for the heights of our rectangles, we're going to take the value of the function at the left endpoints. So here our left endpoints of these 4 subintervals are as follows. They would be x1 is -2, x2 is -1, x3 is 0, and x4 is 1. So for the heights of our rectangles, we're going to take the value of the function at these left endpoints. So starting with our first one, f of -2 is 5. F of -1 is 2. F of 0 is 1. And f of 1 is 2. So to construct our rectangles, well, we're taking the base as each of our little subintervals, and the height is the value of the function at that left endpoint. So we have 4 rectangles shown here, and our area will be approximated by the area of the sum of the area of those 4 rectangles. So here, our approximate area will be the width of our first rectangle, which is delta x, or 1, times the height of our first rectangle, which was 5, plus the width of our second rectangle, which is 1, times the height of the rectangle, 2, plus the width of the third rectangle, 1, times the height of that rectangle, which is 1, and then plus the width of our fourth rectangle, 1, times its height, which was 2. So altogether, we have a value of 10. Now, it can be shown, as we'll see a little bit later in this chapter, that the actual area is 9.3 repeating. So here, just a little note, the true area is equal to 28 thirds, which is 9.3 repeating. So we see that in our second part of this example, by using more rectangles, we got a better approximation of the true area than we did in part A. So let's look at some other ones, get a little more practice with this. So in our next example, we're asked to approximate the area under the curve 2 over x plus 1 and above the x-axis on the interval from 1 to 9 by using rectangles whose height is the value of the function at the left side of the rectangle. So let's take a look at this. We have first, for the graph of our function, something like the following. So if x is 0, our y value is 2. And then as x becomes larger, 2 over x plus 1 starts to decay towards 0. It looks something like this, just a rough sketch. So on the interval from x equals 1 to 9, we're interested in the area of this shaded region. And we're supposed to approximate the area of that shaded region in part A by using two rectangles. So same process as in our last example. For the width of these rectangles, we're going to use delta x, which would be the total length of my interval, 9 minus 1, divided into two equal pieces. So we would have 8 over 2, or 4. So that means for our rectangles, well, we're moving from 1 to 5, and then from 5 to 9. So each of these little subintervals has equal width delta x, which was 4. Now, for each of these subintervals, so here, let's say the subintervals are from 1 to 5 and 5 to 9. Now for each of these subintervals, we're going to take the left endpoint of that interval, and the value of the function at that left side of our interval will be the height of our rectangle. So for f of 1, we have some value. We're going to take that as the height of our first rectangle. And then for f of 5, we have the height of our function, and that will be the height of our second rectangle. So adding up the area of those two rectangles, we have an approximation of our shaded area. So let's look at these left endpoints. Here, the left endpoints are x1 equals to 1 and x2 equals to 5. So the heights of our rectangles are given by the value of the function f at these endpoints. F of 1, which is 2 divided by 2, or 1, and f of x2, which was 5, so we would have 2 over 6, or 1/3. All right. So our area of this shaded region is approximately the sum of the areas of these two rectangles. So the base of each one was delta x, or 4, times the height of our first rectangle, which was 1. Base of the second rectangle is also 4 times its height, which was 1/3. So we have 4 plus 4/3. 4 would be 12/3 plus 4/3 is then 16/3. All right. So in part B, we're told to, again, approximate the area of this shaded region. So let me draw a little sketch to keep track of what we're doing here. So we have the same function on the interval from 1 to 9. And here we're using 4 rectangles. So to get the width of each rectangle, delta x, we take the length of our interval from 1 to 9, so that is 9 minus 1, and divide it into 4 equal pieces. So this would give us a width of 2, which means that the subintervals for our rectangles are going to be from 1 to 3, from 3 to 5, from 5 to 7, and from 7 to 9. So here we are dividing into these subintervals of equal width 2, or of equal length 2. Now, to determine the height for each of our approximating rectangles, we're choosing the left endpoints of each of these subintervals. So those would be x1 equals to 1, x2 equals to 3, x3 equals 5, and x4 equals 7. So for each of the 4 subintervals that we just found, we're choosing the left endpoint as being used to determine the height of our rectangle. Now, the height of the rectangle is given by the value of the function at those left endpoints. So we have something that looks like the following. And our area of this region is approximated by the sum of the areas of those 4 rectangles. So let's find these heights. Here, the height of the rectangles are the value of the function at the endpoint. So here, f of 1 is 1. F of 3 would be 2 over 4, or 1/2. F of 5 is 2 over 6, or 1/3. And f of 7 is 2 over 8, or 1/4. So the area of this shaded region is approximately the sum of the areas of these 4 rectangles. Now, each one has a base of width 2. The height of the first one was 1. So plus the base of the second one, 2, times the height of that second rectangle, which was 1/2, plus the base of the third, which was 2, times its height, 1/3, plus the base of the fourth, which was 2, times its height, 1/4. So we are left with, after simplifying, a 25 over 6. All right. So these values, just for comparison's sake, this 16 over 3 that we found in part A is 5 1/3, or 5.3 repeating. The 25 over 6 that we found in part B is 4.16 repeating. And the true area, which we'll see how to find a little bit later in our chapter 13 material, is approximately 3.22. So we see again in part B, we got a little better approximation of that true area by using more rectangles. So let's look at one last example. So in this next one, we're told to consider the region below the curve f of x, which is x divided by 2, and above the x-axis on the interval from 0 to 4. And we're told again to let xi be the left endpoint of the ith subinterval. So here, let's sketch our region. So in the xy plane, we're looking at the graph of x over 2, which is a line through the origin of slope 1/2. So it passes through 0, 0, and then we're looking at this on the interval from 0 to 4. So the height at our right endpoint is 4 over 2, or 2, and we're looking for the area of this shaded region. So in part A, we're told to use 4 rectangles to approximate the area of this region. So here we would let the width of our rectangle, delta x, be the length of the interval from 0 to 4, so that is 4 minus 0, and we're dividing it into 4 equal pieces. So each rectangle will have a length of 1, which means that the subintervals that we're interested in are from 0 to 1, from 1 to 2, from 2 to 3, and from 3 to 4. So here we're taking our interval from 0 to 4 and dividing it into 4 equal subintervals, each of length 1. And we're told again to let x sub I be the left endpoint of the ith subinterval. So our left endpoints for these 4 rectangles are as follows. The first one, x1, would be 0, x2 is 1, x3 is 2, and x4 is 3. Okay, so taking those endpoints as the heights of our rectangle, we have the following. So here, the heights are the values of the function at the left endpoints. So that would be f of 0, which is 0, f of 1, which is 1/2, f of 2, which is 1, and f of 3, which is 3/2. So illustrating here, well, the height of our first rectangle is nothing. The height of the second rectangle is 1/2. Height of our third rectangle is 1. And the height of our fourth rectangle is 3/2. So by adding up the area of those rectangles, we have an approximation for the area of our shaded region. So here, that area is approximated by taking the value of the width of our first rectangle, which was 1, times its height, 0, plus the base of the second rectangle, which was 1 times its height, 1/2, plus the base of the third rectangle, 1 times its height, which was 1, plus the base of the fourth rectangle, which was 1, times its height, 3/2. So altogether, we're left with 4/2, or 2 plus 1, which is 3. So this would be an approximation of that area. And then in part B, we're told to find the definite integral of f of x dx on this interval from 0 to 4. So that is the true area of this shaded region, by making use of a formula from geometry. So in this example, we notice, if we look at the sketch of our region, under the graph of x over 2, so again, a line of slope 1/2 passing through the origin, on 0 to 4, we see that this is just a triangular region. And we know how to find the exact area of a triangular region. It's given by 1/2 base times height. So here, our area, which is represented by this definite integral, is given by 1/2 of the base times the height of our triangle. So here that would be 1/2 of, well, the base of our rectangle is length 4 from 0 to 4. And the height of our rectangle is 2. We're moving from 0 to 2. So we have a value of 4 for the true area of this region. So depending on what the shape of our region is, we might be able to find a value for the a true value for the area, maybe using some formula from geometry. Or for our first couple of examples, if our region is a little abstract shaped, then we can approximate the area by using this Riemann sum, that is by using approximating rectangles. So in our next few sections, we'll learn how to calculate the true area by making use of anti-direction.